In the previous video, we carried out exploratory analysis on the following data about the earnings of graduates 5 years after they have left university. We are given what course they studied and their gender. We identified our variables, constructed a design matrix, constructed side-by-side box plots to see how our predictor variables behaved independently, and constructed an interaction plot to see how they behave together. We will now test for significance using two-way ANOVA. To see why this is the correct test, we first formulate our null and alternative hypotheses. We will be testing 3 separate hypotheses shown here. The first hypothesis concerns gender. The null hypothesis is that the mean earnings for males is equal to the mean earnings for females. However, if we find a p-value below our 0.05 significance level, we reject this and accept the alternative hypothesis that the means do not equal. The second hypothesis concerns course. The null hypothesis is that the means between courses are not all equal. If we find a p-value below 0.05, we reject our null and accept the alternative hypothesis that at least 2 of these means do not equal each other. The third and final hypothesis concerns the interaction between course and gender. The null hypothesis states the influence of gender on earnings is independent of the influence of course on earnings. If we find a p-value below 0.05, we reject this and accept our alternative hypothesis that gender and course interact to have an effect on earnings. From the previous video, we know we have 2 categorical predictor variables that influence a quantitative response variable. We are interested in the 8 blocks we produced in our design matrix shown here. As we have more than 2 blocks, we use ANOVA, and because there are 2 predictor variables, we use a two-way ANOVA. We can now test our data using the following code. Our ANOVA table is produced here. The top row relates to our first hypothesis. It gives a p-value of 0.4716. This is nowhere near significant. In fact, it shows an even chance that the observed differences in means occurred at random. Thus, we do not reject the null hypothesis. The next row relates to our second hypothesis. It gives a p-value of 2.76 times 10 to the power of minus 9. This is way below our significance level of 0.05, so it is highly significant. This means we reject our null hypothesis and accept our alternative hypothesis that mean earnings are significantly different between at least 2 courses. The third row relates to our third hypothesis. It gives a p-value of 0.1764. This is more significant than the result for gender, but it is still above the 0.05 significance level, so we cannot reject our null hypothesis. The 0.1764 value means we have just under a 1 in 5 chance of this apparent interaction occurring at random. The 0.05 significance level means that to reject the null hypothesis, we want the chance that the observed differences in means occurred at random to be below 1 in 20. We now need to ask what follow-up tests we should carry out. For our first hypothesis, our exploratory data suggested there would not be much difference in earnings between males and females. Our ANOVA results confirm this, giving a p-value of 0.47. There is no need to do further testing on this hypothesis, and we conclude that there is no difference in earnings based on what gender you are. For our second hypothesis, our exploratory data suggested there would be some difference in the mean earnings between courses. A very low p-value has confirmed this, and the difference in means is highly significant. Due to this, we now wish to estimate the effect size. We have 2 choices here. We can use contrast, which will look at a single comparison of means, i.e. the difference of means for a single course against all the others. So this would see if the difference in means for maths against all the other courses was significant, etc. Or we can use Tukey-Kramer, which will calculate the effect size for pairwise comparisons. For our third hypothesis, our exploratory data suggested there might be some interaction. However, the p-value suggests there is none. We may want to see what the chances are that we have made a type 2 error, that is, falsely accepting the null hypothesis. To do this, we are required to make a power calculation. If our power is low, we may ask how many people we would have needed in our sample to ensure we have a less than 20% chance of making a type 2 error. The following document sums up what we have achieved in this video. We stated our hypotheses, we chose the appropriate test for our data, we calculated and interpreted the p-values, and we have looked at what follow-up tests we need to carry out.